Hello, everyone, and welcome back to another deep dive.
Yeah.
Today, we are cracking open Unit 5, Coordination Compounds.
A big one.
A very big one. And I have to be honest with you, I was looking through the source material for this, sections B1 to B4, and I found a bit of a chemistry mystery that's been, well, it's been bothering me.
Oh, I love a good chemistry mystery. It is usually the best way to learn, actually. What did you find?
Okay, so picture this. You're in the chemistry lab, and on the shelves, you have a beaker of potassium ferrocyanide. Now, we know from the formula, it's got iron right there in the center.
Correct, yes. It's a classic iron complex.
But here's the strange part. It is this deep, beautiful yellow solution. And you can dump almost anything into that beaker. Other chemicals, you name it. And it just sits there. It stays yellow.
Uh-huh.
It's like the iron is wearing a suit of armor. It is completely invincible. You cannot touch the iron inside.
It's like tank, basically.
Exactly, a tank.
Yeah.
But then you walk over to the next workbench. You take a beaker of ferric chloride. This also has iron in it, right?
Yeah.
You dissolve it in water, you get that pale purple color. But if you add just a tiny drop of ammonia to this one, boom, instant reaction.
The color changes immediately.
The iron reacts instantly. The whole thing just falls apart.
Completely.
So my question, and really our mission for this deep dive is this. We have two beakers, both contain iron. Why is one functionally bulletproof and the other one is so fragile that it reacts if you even look at it wrong?
Precisely.
That is the million-dollar question, isn't it? And honestly, what you have just described is the perfect entry point. It's not just some random lab trivia. It is the fundamental difference between a stable complex and an unstable one.
So that is our topic today, the stability of coordination compounds.
That's it, exactly. Stability of coordination compounds. And, before any of our listeners tune out thinking, oh, great, more definitions to memorize, I want to be very clear about why this matters.
Okay.
This is not just about colors in a beaker. This is, well, it's a science of persistence.
Persistent. Yes. This concept, it allows us to predict the future of a molecule. It tells us whether a compound is going to survive in the chaotic environment of a solution or if it's going to disintegrate the moment things change slightly.
Wow.
It is the difference between a medicine that cures you and a poison that kills you.
Okay, you have definitely raised the stakes there.
Yeah.
From beakers to life or death. So let's unpack this. When a chemist says stability, what are they really talking about?
Let's strip away all the textbook jargon for a moment. We need a zero-level explanation. At its absolute simplest level, stability is basically grip strength.
Grip strength, like how hard I'm squeezing a cricket ball.
Very similar, yes. Think about the structure of a coordination compound. You have the central metal ion, like the iron in your example, and it is surrounded by these other molecules called ligands.
Right.
Stability is just a measure of how tightly that central metal is holding on to its ligands.
Okay, I can visualize that. So in my yellow beaker, the ferrocyanide.
In that beaker, the iron has a death grip on those cyanide ligands. It is holding on so tightly that even if other molecules bump into it, the iron refuses to let go. That is what we call a stable complex.
And the other one, the ferric chloride in water.
That is a weak grip. It is like having sweaty palms. The iron is holding on to the water molecules, but barely. So if a new molecule comes along, like the ammonia you mentioned, that looks even a little more attractive, the iron just drops the water and grabs the ammonia immediately.
So stability is really just resistance to a breakup.
That is surprisingly accurate. Yes, It is the resistance to dissociation.
I really like this hand-holding image. Let's push that a bit more for everyone listening. So imagine you are watching two couples holding hands.
Okay.
Scenario A is, it's like a professional bodybuilder holding hands with another very strong person. Fingers locked tight.
Yeah.
You could try to pull them apart, but it's not happening.
Right, a huge energy barrier to break that bond.
That's our stable complex. Then you have scenario B. This is two people just barely touching their fingertips together.
Right.
A gentle breeze flows past.
And they separate.
Exactly. Or someone just walks between them. That's the unstable one.
That is a perfect analogy. But now, as a science student, you have to ask the next logical question.
Why? Why is one holding tight and the other is barely touching? Is the metal just lazy?
No. Atoms don't make choices like that. It's pure physics. And this is where we get into the underlying behavior. It comes down to a principle we call HSAB.
HSAB. Sounds like a secret government agency or something.
It stands for hard and soft acids and bases. It is a classification system.
Okay, let's break that down. We know acids and bases, but hard and soft, or if we're talking about texture, like a pillow versus a rock.
Not physically soft like a pillow, but the analogy does help. Think of it in terms of the electron cloud, the outer shell of the atom.
Okay.
A hard species is small, it's compact, and it usually has a high positive charge. The electrons are held very tightly. They are not squishy.
Okay. Small, dense, high charge. Like a little glass marble.
Exactly. That is a hard acid, like iron in the +3 state. Fe3+.
Got it.
Now, a soft species is the opposite. It is larger. The electron cloud is big, it's fluffy, it is easily distorted,
Like a sponge or a water balloon.
A water balloon is a great image for a soft species. Perfect. So here's the golden rule you need to remember. Like, prefers like.
Prefers like.
Yes. A hard metal, the marble, will form a very strong, stable grip with a hard ligand, another marble.
And I'm guessing soft prefers soft.
Exactly. The water balloon metal wants a water balloon ligand. When you match them up hard with hard or soft with soft, the grip is incredibly strong. The stability is high.
But what happens if you mix them? A hard with a soft?
It's a mismatch. The interaction is weak. That grip is going to be slippery, unstable. It is like trying to use sticky tape to stick a marble to a wet balloon. It just doesn't hold.
So going back to my mystery beakers.
Yeah.
The iron in the ferrocyanide.
In that specific case, the iron and the cyanide are a great electronic match. It's a very compatible relationship. That is why you get that death grip.
Whereas the iron and water in the other beaker.
Not a great match. Plus, water is a neutral molecule, whereas cyanide is a charged ion. The attraction just isn't there in the same way. It is a fingertip touch situation.
This makes so much sense. It's basically chemical compatibility dating.
It really is. Nature wants a good match.
Okay, so we get the concept. Grip strength, compatibility. But our listener has an exam to write. They can't just write, it's like dating on the answer sheet, right?
No, please do not do that. The examiner will not be impressed.
So give us the textbook definition, the anchor definition for the exam.
Here's what you need to memorize. The stability of a coordination compound is its resistance to dissociation or ligand substitution.
Resistance to dissociation.
And we actually quantify this. We don't just say strong or weak. We use a number. It's called the stability constant, and it's written as Kf.
KF.
The F stands for formation. A higher Kf value means a more stable complex. It just means the ligands are held more tightly.
Actually, hold on a second. You just said something that always trips me up. You said formation. The symbol is KF, but the notes explicitly warn us not to confuse formation with stability. That sounds contradictory.
It is the classic trap. I am so glad you caught that. This is where so many students lose marks.
Okay, unpack it for me.
Just because a complex can form does not mean it is stable.
Give me an analogy.
Okay. Imagine you build a house of cards. Did you form a house?
Yes, technically.
Is it stable?
Definitely not. If someone sneezes, it's gone.
Exactly. You formed it, but it lacks stability. In chemistry, a reaction might happen fast, that's formation, but the product might fall apart just as fast. That's instability. When we talk about Kf and stability, we are only talking about persistence.
Persistence.
Once it is built, does it stay built?
I love that. Don't confuse existence with persistence.
That is the key to the whole unit, really.
Okay, I want to pivot to something more visual. We have done the hand-holding, but the source material mentions magnets. I think this could really help visualize the process.
The magnet analogy is my absolute favorite mental model for this topic. It's brilliant.
Walk us through it.
Okay, imagine a plastic container. Inside, you have a central magnet. That's your central metal ion.
Okay.
And you have a bunch of small metal paper clips stuck to it. Those are your ligands.
Right. I'm picturing a magnet ball covered in paper clips.
Now, a stable complex is like a high-powered industrial electromagnet. Those paper clips are slammed against the surface. You can shake the container vigorously.
Which represents energy in the solution.
Exactly. And those paper clips are not moving. They're locked in tight.
Okay.
Now imagine an unstable complex. This is like a cheap, weak fridge magnet. The paper clips are sticking, sure. But if you shake the container even a little bit,
They fly off.
they fly off. Or if you toss in a stronger magnet.
The paper clips will detach and stick to the new thing instead.
Precisely. That is what we call a labile complex in chemistry. It is reactive because its grip is too weak to hold its structure.
Labile. That's the technical term for unstable.
Yes, we usually say stable versus labile. Labile just means prone to change.
Got it. Okay, I want to try a mental movie exercise to really cement the image so you can recall it in the exam hall.
Let's do it.
Listeners, if you can, close your eyes for a second. Go back to those two beakers. Beaker 1, potassium ferrocyanide. Deep yellow.
Visualize that single iron atom floating in the center.
Now, see the 6 cyanide ligands surrounding it. But in this stable complex, I want you to see them connected to the iron by thick, glowing steel cables.
Heavy-duty cables, the tension is high, nothing is moving.
Now imagine a stray ammonia molecule swinging by. It tries to cut in, it bangs against the steel cables. What happens?
Nothing at all. The cables are too strong, the ammonia just bounces off, the structure persists.
Now cut to beaker 2, the ferric chloride. Pale purple. See the iron atom. But this time it's connected to water molecules.
Not by cables. Visualize thin, wispy spider silk.
Barely attached. A gentle wind could break it.
Now that same ammonia molecule swims up. It just brushes against the spider silk and snap.
The thread breaks.
The water drifts away. The ammonia grabs the iron, and the color of the solution shifts instantly.
That is a powerful image. It really helps explain why unstable doesn't mean doesn't exist.
Yeah.
The spider web exists. It's just very fragile.
Exactly.
So we have covered the theory. But I always have to ask, why do we care? Does this actually impact the real world?
Oh, absolutely. This concept saves lives. Literally.
Go on.
Have you heard of chelation therapy?
I have heard the term. It is used for heavy metal poisoning, right? Like if a child accidentally swallows lead paint chips.
Right. Which is a terrifying situation. When lead gets into the body, it's what we call a soft acid, and it loves to bind to the sulfur in our enzymes and proteins.
So it basically gums up the body's machinery.
It poisons the enzymes. Now, to save the patient, doctors inject a chelating agent, usually something called EDTA.
Okay, so how does EDTA help? Why does the lead go to the EDTA?
It works entirely because of stability constants. EDTA is designed to form a much, much more stable complex with lead than the body's proteins do.
Wait, so it's a competition?
It is a massive tug of war, basically. The body is holding the lead with, let's say, one hand. EDTA comes in and grabs the lead with 6 hands. It wraps completely around it.
6 hands.
Yes. EDTA is a hexadentate ligand. It has 6 teeth or binding points. This is called the chelate effect. A ligand that grabs with multiple hands will always be more stable.
I see. So because the EDTA lead grip is stronger, the stability constant is higher, it literally rips the lead away from our body's proteins.
It steals it, it wraps it up in a tight cage that the body can't interact with, and then you just excrete it out safely.
That is incredible. So the medicine works just because it's stickier than the poison.
It is all about the KF value. If the EDTA complex was not more stable, the lead would not move. The patient would not get better.
That puts a whole new perspective on those numbers in the textbook.
Speaking of numbers, I have one counterintuitive fact that usually blows students' minds.
Hit me.
When we say stable versus unstable, you probably think the difference is small. You know, like one is a 7 out of 10 and the other is a 4 out of 10.
Yeah, that is how I imagine it. Stable versus slightly less stable.
Actually, the difference is, it's astronomical. For our stable friend, ferrocyanide, the KF is roughly 10 to the power of 42.
Whoa. 10 with 42 zeros.
Yes. A number so big, it's almost meaningless. Now, for the unstable complex, the iron with water, the value might be around 10 to the power of 3.
So 1,000.
1,000 versus 10 to the power of 42.
That is not just a difference. That is a different universe.
Exactly. It's the difference between a mountain and a grain of sand. That is why the steel cable analogy holds up. Stable complexes are profoundly locked in.
That really drives it home.
The numbers don't lie.
Okay, we are coming up on time. I want to make sure our Class 12 listeners have their cheat sheet ready for the board exams.
Yes. Let us boil it down to 4 exam-safe clarity lines. If you write these, you get the marks.
Point number 1.
The definition. State clearly. Stability is the measure of resistance to dissociation. And you must mention the stability constant, KF. Higher KF equals more stable.
And the tieback is, if you see a high number, that complex is not breaking apart.
It's the steel cable. Point number 2. The HSAB principle. If the question asks why something is stable, check the metal and the ligand. Hard matches hard, soft matches soft.
Like prefers like. That is the reason for the grip strength.
Correct. Point 3. The chelate effect. If you see a ligand like EDTA or oxalate something with multiple binding sites, it is almost always more stable.
Multiple hands hold tighter than one hand. Got it.
And finally, stable versus labile. Do not confuse unstable with non-existent. Unstable complexes exist. They are just very reactive.
That's the spider silk. It's there, but it breaks easily.
You've got it.
This has been a really, really clarifying dive. I honestly did not realize how much drama was happening inside a simple beaker.
It's a battlefield down there.
So let's wrap this up with a short summary of our journey today.
Sure. We started with the core idea. Stability is just resistance to dissociation. It's the grip strength.
We visualize this with the analogy of the magnet. A strong magnet holds the pieces tight, or the beaker with thick glowing ropes for stable, versus thin threads for unstable.
Then we had the example of chelation therapy. EDTA cures poisoning because it forms an ultrastable complex with lead, stealing it away from the body.
And finally, the key rule. Always look for the stability constant, Kf, and remember the chelate effect. Higher numbers and more teeth mean more stability.
A perfect summary.
Before we sign off, is there one big thought you want the listener to walk away with?
I think just this. Chemistry often feels like memorizing rules. But if you understand stability, you understand the motivation of the universe.
The motive.
Nature is lazy. It always wants to be in the most stable, lowest energy state. It's always looking for those steel cables. If you can look at a reaction and identify which combination is most stable, you can predict what will happen. You don't have to memorize it. You can foresee it.
It's not magic, it's just nature seeking a nap.
Exactly. Seeking the strongest grip so it can stop moving.
I love that. Well, thank you for walking us through the mystery of the invincible beaker. I am definitely going to be visualizing those glowing ropes from now on.
Just watch out for the spider threads.
That is it for this deep dive. Thanks for listening, and good luck cracking Unit 5.